something invisible hit Earth on December 27, 2004. From 50,000 light-years away, it compressed our atmosphere in 200 milliseconds. Nobody noticed. At 21:30 UTC, every gamma-ray satellite in orbit saturated, all at once. Swift, RHESSI, integral, 6 satellites simultaneously. The event lasted 18 seconds, but the peak, just 200 milliseconds. This was not a solar flare, too energetic, too brief. Not a supernova, too short. Supernova last days, not a gamma-ray burst. Those are extragalactic, millions of light-years away. This one was traceable. Instruments pinpointed it within our galaxy. In Sagittarius, 50,000 light-years away. The source was already cataloged. Not a star. A magnetar. SGR 1806-20. SGR 1806-20 had been quietly observed for years, flickering with soft gamma bursts. Then, ground stations worldwide measured the ionosphere compressing during the 200 millisecond peak. VLF frequencies bent. The ionosphere pushed down by tens of kilometers. Time lock to the exact moment of the burst. This is not an inference. This is a direct measurement. The event physically touched Earth's atmosphere. Communication systems using low-frequency radio noticed the shift. GPS satellite signals showed brief distortions during the peak. Some magnetic field detectors on Earth registered a transient perturbation. The atmosphere responded to a burst from 50,000 light-years away. Photons had traveled the distance across our galaxy. Then they touched us. Photons left Sagittarius 50,000 years ago, when humans built the first cave shelters. When they arrived, we had gamma-ray telescopes waiting. We expected magnetar bursts. Not this bright, not from this far. Something 50,000 light-years away had just touched Earth. The source? A neutron star with a magnetic field a quadrillion times stronger than Earth's. A magnetar forms when a supernova collapses, just short of a black hole. The core compresses into just 20 kilometers wide. A teaspoon of its material weighs 1 billion tons. But the truly extreme part? The magnetic field. 10 to the 15th Tesla, a quadrillion times Earth's field. Strong enough to warp atomic structure itself. Only about 30 magnetars are known in our entire galaxy. They are rare. They form when supernovae have unusually high angular momentum. The collapse spins the field tighter. Once formed, a magnetar spins rapidly at first, several times per second. Its magnetic field slows the rotation over millions of years. During this slowing, the field lines occasionally get tangled and knotted. When the tangled field ruptures, the magnetar's crust cracks, a starquake. It releases accumulated magnetic energy in a burst. Most are minor, producing soft gamma repeaters, SGR events. That's how SGR 1806-20 got its name, through decades of minor bursts. But every few centuries, a magnetar undergoes a giant flare. The 2004 event was the largest giant flare ever recorded. It released more energy in 200 milliseconds than our sun releases in 100,000 years. That energy propagated outward as gamma photons. 50,000 years later, those photons arrived at Earth. The magnetar's crust cracked. The field tangled. Energy released. In 0.2 seconds, energy equal to 100,000 years of our sun's total output flew outward at light speed. 50,000 years later, at 21:30 UTC, December 27, 2004, that wavefront reached us. A magnetar starquake. How do we know it compressed our atmosphere? We measured it. Precisely. At ground stations in Antarctica, Alaska, and Australia. These VLF waves bounce off the ionosphere and travel long distances. They are used for submarine communication. When the magnetar burst hit, the ionosphere pushed downward by tens of kilometers. The waveguide narrowed. This changed the VLF wave propagation timing measurably. Terasawa and colleagues in 2005 documented the phase shifts precisely. The measurement was published in Nature. The compression was real. The peak compression correlated exactly with the peak gamma flux from the burst. This is not a computer simulation. This is a physical measurement. The atmosphere absorbed a fraction of the gamma energy. That fraction was enough to compress it. The remaining gamma photons continued through the atmosphere and reached the ground. But at the ground, they were harmless, diffused, absorbed. Nobody on Earth's surface felt anything. No health effects recorded. In the 50,000 light-year distance protected us, the atmosphere absorbed most radiation. Only satellites detected the burst directly. But the compression is unmistakable in the data. In 200 milliseconds, it released more energy than our sun releases in 100,000 years. 6 satellites saw the initial burst, 15 more saw the echo. 21 instruments agreed. The measurements aren't estimates. This event was recorded, quantified, and timed. Palmer and colleagues published the full analysis in Nature in 2005. Israel and colleagues confirmed the timeline in the Astrophysical Journal Letters the same year. Within seconds, the ionosphere relaxed back to its normal position. The atmosphere absorbed the shock. VLF communications and GPS distortions cleared within an hour. Recorded, measured, published. This is not speculation. SGR 1806-20 was 50,000 light-years away. That distance saved us. But if the same event had occurred at 100 light-years, gamma flux 250,000 times stronger. The ozone layer. Not destroyed, but damaged. At 30 light-years, the impact becomes serious. Global cooling from ozone loss. UV radiation reaching the surface would increase dramatically for years. Plant life would be damaged. Marine plankton, sensitive to UV, would die off. The food chain would be disrupted at its base. At 10 light-years, we cross into mass extinction territory. The ozone layer would be nearly destroyed, direct UV exposure at the surface. The atmosphere partially ionized, weather patterns disrupted for decades. Some estimates suggest 60–70% of surface species would die within a year, comparable to Earth's greatest extinctions. The Ordovician, 450 million years ago, may have been caused by a nearby gamma-ray burst. At 3 light-years, gamma flux strips Earth's atmosphere within hours. The surface becomes uninhabitable. No known magnetar is that close, but magnetars aren't the only gamma source. The 774 AD Miyake event, that cosmic ray spike locked in tree rings, may have been a nearby gamma flash. At 10 light-years, a flare like this triggers mass extinction. In 2012, researcher Fusa Miyake found massive cosmic radiation events locked in tree rings, carbon-14 spikes from 774 AD, 993 AD, 54 AD BCE, solar superflares, magnetar bursts. We don't know the source. If a Miyake-scale event hit today, every satellite would fry. Every power grid would collapse. And for a magnetar burst, the photons arrive first. There's no warning system for the next one. SGR 1806-20 is one of about 30 known magnetars in our galaxy. Some are closer. All of them can burst. 1E 1048.1 5B937 sits 9,000 light-years away. SGR 0501+4516 is even closer, just 5,000 light-years. Each has produced smaller bursts. None have unleashed a giant flare. Yet. But magnetar prediction is impossible. We don't know when the next giant flare will strike. The starquake mechanism is chaotic, driven by stress accumulation in the crust. We can track magnetars, observe their pulses, but never predict their bursts. And some remain invisible. Estimates suggest hundreds of dormant magnetars in our galaxy. hidden from us entirely. They are cold, quiet, and dark until they suddenly burst. One of them could be closer than 5,000 light-years. We would not know. Even the identified ones are largely unpredictable. So the truth is, there is no gamma-ray defense system. There is no way to detect a magnetar burst before its photons arrive. Photons travel at light speed. Any warning comes after they hit. Which raises a darker question. Are there stars that produce something worse than a magnetar flare? A magnetar giant flare releases 10 to the 46 joules. A gamma-ray burst releases 10 to the 47, 10 times more. And those come from Wolf-Rayet stars, massive stars nearing supernova. Wolf-Rayet 104. In Sagittarius, 8,400 light-years away. Its polar axis is pointed directly at Earth. SGR 180620 was 50,000 light-years away and still touched our atmosphere. WR 104 is 6 times closer, and its beam is aimed at us. When it collapses, it will burst. Next, the gamma-ray burst aimed at Earth.